ROID is an instant film photography studio where you come in, you get photographed on a vintage film cameras, and you walk out with a physical frame keepsake. It's a lovely concept, but like any business, it has its problems. Over the next few minutes, we will show you how we model that problems with simulation and landed on recommendation backed by numbers rather than gut feel. Before we get started, let's give you a virtual tour of what a customer can expect when visiting ROID.
I would like to show you a clear picture of how ROID workflow works. So first, the customer enters the shops and start by meeting the receptions, where the reception will recommend the products and customers select their film products. After that, we'll walk into the preparation stage. So here at this stage, the customer will take time to choose the props and think of the pose. Then heading into the photo sections. After finish the photo sections, the staff will hand you the decoration thingy to decorate the cards while waiting for the film to develop. And then go to the decoration stage. Here is one station and another one is there. As you can see, in this room have limited space, so it will maximum of 4 groups. And after the customer finish decorations the film, they will heading back to the staff to packaging the products. But also the film need to be finished developed. And also the staff will adopt or sharing the photo here with the customer. And the last stage is proceed the payment before leaving. And that's all of the ROID workflow.
So ROID's customer comes in a good mood, and we don't want to ruin it by keep them waiting for so long. But here's the issue. The current system allows 3 bookings every 30 minutes, not including walk-ins. So whenever there is an unexpected customers, or when there's a process delay, queues time form at a certain station, such as photo shoot station.
This can cause customer dissatisfaction, overtime labor, overloaded bottleneck at key stations. We therefore want to create a discrete event simulations in order to find out what causes waiting time and where waiting time is formed most. Is one receptionist too little, or do we have to add more photographer or spread out the booking time more? We will simulate the best scenario to find which one suits the ROID most.
To link and prove our proposed problem with evidence, we use CCTV footage to confirm that customers wait or receive service at multiple stations at the same time, showing congestion as seen in the picture here. We also collected service time data at each station for different group sizes and service types to build triangular distributions for the simulation. Based on this evidence, we deducted ROID's waiting time problem to be mainly caused by peak hour arriving clustering, limited staff flexibility, station bottlenecks, and the lack of a structured priority queue for bookings. Before we go further, it's worth knowing the menu, because the product type drives everything in our model. ROID offers 9 products as shown on the screen, and you're probably wondering why this matters. It's because a quick Polaroid and a multi-shot collection set take very different amounts of time to shoot, develop, decorate, and share. So when we model the studio, we can't treat every customer the same. Each product carries its own service time profile. Please keep these 9 names in mind as they come back when we build the simulation.
We built our probabilities from the studio's last 500 customers. From those records, we formulated discrete probability distributions for the factors that shape a visit. For example, group size, booked versus walk-in, weekday versus weekend, the service type, and the schedule time. So when our simulation simulates a customer, it draws each of these traits in the simulation. For the station service time, we use a triangular distribution. Each product has its own block of these min, max, and mode values per station, which is further broken down by group size and whether they are booked or walk-in. The 2 service time affected by these variables are preparing time and shooting time.
Next is model part 1, which is Monte Carlo simulation. This is where it all comes together. We simulated 1,000 customers. It estimates the expected flow time for each product, broken down by group size and booking status. Let me walk you through what is going on here. First is the model draws the discrete traits we just built. Day type, booking type, group size, and service type. Each column has its own probability. Then, for every station, it draws a service time from that station's triangular distribution from the previous sheet. Same as discrete distribution, the way we sampled the triangular distribution is with 1 random number per station. If the random draw is small, the time lands on the rising side between the minimum and the mode. If it's large, then it lands on the falling side between the mode and the maximum. After we finish everything, run that 1,000 times and we'll get a stable picture of how long each product really takes. As a result of after running simulation, we get an average flow time of approximately 40 minutes per group of customer. And the cell you see right here simply means that particular product and group combination never came up in the 1,000 draws. Model part 2 simulates 40 customer groups based on the studio's real operation. And this time, we don't just sum service times, we actually queue them. We sort all these 40 iterations by their actual arrival time. Then using queuing formulas from our reference and self-study, we calculate the starting time, end time, and waiting time at each and every station. Because a customer can't start at a station until both of the previous customer has cleared it. On top of that, we enforce the studio's real constraints, a maximum of 4 groups in a decoration room, 3 bookings per period, the number of staff, and the fact that a photographer and receptionist can cover each other's job at a certain stations. All of that runs through a VBA macro. By just pressing one button, it simulates the whole day operation of the studio. And if we want to test different scenarios, we can simply just change the input and press simulate again. It will automatically simulate the new scenario.
We have collision checker for photographer receptionist, and we also check if there is any overtime happen in the workflow. For photographer check, the formula looks at their time photo is happening and asks, is the photographer doing anything else right then? The formula uses some product which simply count how many other tasks overlap the photo time window. It does this by checking for every task whether it starts before the photo ends and ends after the photo starts. If both are true, the two overlap. It counts other photos and any reception, sharing, or payments the photographer did and subtract one so the photo doesn't count itself. And for the receptionist, it works the exact same way, but for the receptionist, the formula first checks if the customer was served by the receptionist. If so, it used that the same sum product overlap count to see whether the receptionist was handling another job at the same time. More than zero overlap means collisions, and zero means okay. And lastly, the overtime checker. This formula is a simple time comparison. The formula takes the customer payment end time, the moment they finish, and compare it to 7 o'clock using a if. If the finish time is later than 7, it calculates how many minutes over by subtracting 7 o'clock and multiplying by 1440 to turn the difference into minutes.
For part 2 of the model, we tested 6 different scenarios. Firstly, the normal scenario with 1 photographer and 1 receptionist. For 2 and 3, we added 1 photographer and 1 receptionist respectively. Scenario 4 simulates a situation where appointments per slot are reduced from a maximum of 3 to 2. And Scenario 5 tests a situation where we reskill a receptionist to be capable of doing photography. And Scenario 6 tests a combination of reskilling and adding 1 more photographer. As expected, Scenario 6 reduces the average flow and waiting time the most. From the baseline scenario, photography appeared to be the bottleneck station, but this scenario would almost completely solve it. However, we would need to further evaluate if it's worth the cost of hiring and training a new employee. So here's a deeper analysis. To determine whether a scenario was effective in helping ROIDs reduce waiting times, we looked at 3 main factors. Firstly, we looked at total waiting occurrences across all stations. Then we looked at whether the scenario would increase or decrease the total amount of customers ROIDs can host per day. Lastly, and most importantly, we considered the cost per minute of average waiting time reduced. And based on these 3 criteria, Scenario 2 seems most effective as it reduces waiting time occurrences significantly while being more cost effective than Scenario 6.